Hello everybody. This video is being made for the purpose of CS206 final project. This will be our last report. This is report number 8, and in this particular video, I'm gonna follow up with the work that I had done so far in the CS206 project. So last time that we had done, we had created a fitness function that was able to penalize our overshoot and our error, steady state error. So this was our first fitness function. So we used to simulate our system, and once we did our simulation, we used to acquire the data from that simulation and then measure the overshoot and the error and the steady state error in that system. And the whole purpose of that fitness value was to decrease the overshoot in our system and to decrease the steady state error, because we want our error to be zero or as close to zero as it can be. In this particular video, what I've done is I have introduced another characteristic or property that we want to control in our system, and that is settling time. So if you have run control systems by any chance, you must be aware of the response of a system. So this is a second order response of a system, and there are certain properties that we would like to control in a particular system using a PID controller. And those properties are usually the peak, which is the maximum peak that you would like. Undershoot is also another property that you could see. So you would definitely want these two to be as small as possible, but you want the overshoot to be minimum, because let's say if you have a desired set point, you don't want to uh, overshoot that particular desired point. And the other thing that you want to do is you want to reach your desired system within a frame of within a reference of error, which essentially means that you would like to reach your steady state between fixed errors within a fixed error value. So that's like is usually 5%, which means that once your value is 95% correct or 1.05% correct and has been settled down in that particular system, then you have reached or you are very close to your steady state value, and that is called the settling time. Now usually you would like the settling time to be very small so that your system reaches your desired set point as soon as it can. And so this is the third property that I'm going to be introducing in our system. So essentially from the last one, we have created another fitness function over here, which is now going to penalize the settling time in our system. So you might notice over here right now, the main difference is that we are still heavily dependent on decreasing our steady state error, but now there is also weightage given to settling time. So now settling time is usually measured in seconds, and we are now trying to introduce a settling time ratio, which is that how long did it take for the system to settle down or reach that 2% 5% error. I think in this case it's 2% by default. So the way we are measuring it is like how long did it take to settle down between the 2% close to our value. And so the settling time essentially then tells us that we're so in order to basically measure it in the fitness value, we have taken a ratio out of it, and the ratio is found using this particular formula. So we know that our step system response from previous videos starts at 5 seconds. So initially in 5 seconds we don't do anything, and then we run the simulation for a certain period of time, so that is runtime. We then measure our settling time using step info, which is a MATLAB function, and then we find the ratio, and the ratio tells us how long did it take throughout our duration to reach our desired, or for the system to reach within the desired error limits. And so it's always going to be a ratio, because let's say you're running this experiment for 15 seconds, so you want your system to reach your settling time to be small enough so that you reach your desired point within that error percentage as soon as you can. So this is actually a ratio that we are considering with respect to our system. So if our system, the step time is at 5 and then it runs for further 15 seconds, we're gonna measure the settling time, and then divide it by the runtime, which is 15 seconds. So whatever that time is, with divided by 15 seconds will give us a ratio of how long did it take to settle down. So this is the third part of what we have now invested in our system. So I did a run for this, and what you can see right now is that um, that initially with our runnage, what we did is we were able to get a population as seen before, but now the generations are 20. So we have created 20 generations with a population of 10. And as similar to the previous videos, we ran this simulation for 10 generation for 10 individuals, and then we took the highest individual in that particular generation, then we mutated it, and then the mutation process is as similar before. So the way we mutate it, as it was described in the previous video, where we take the new mu from the highest population over here and make it the new mu, and then with respect to that we are able to now reach new values of kp and ki. And so this particular fitness function was now introduced, and the whole purpose of this fitness function is to reduce the settling time as well. And without further ado, I have run the simulation for 20 generations. I'm not going to run this video because it's just going to take so much time. There are some error in this particular fitness function that I have not figured out. So these NaN values are not accurate. There must be some problem in the way these fitness values are being calculated. But as I'll show you in the future, what happens right now is we're going to go through this plot data. So we have saved all the results from this particular test, and I'm going to describe certain results that are very useful in this particular system. So if you run these things, we're now going to get graphs, and I'm going to go through each graph as much as I can. Okay, so the very first graph shows you the last results. So fitness underscore value. So the first graph shows you the fitness value of the last generations, because that we can see that these are quite high. So this shows you the fitness of each individual in the last generation. So there should be 10 values over here. One of them is NaN, so it's not plotted, but these are the best possible values that we could achieve for our last generations, and these are particularly good. So you can see that they range from 0.78 to 0.87. So I mean, these are quite good individuals in our population. The next graph that I have drawn is the kp and ki values with respect to each generation. So each individual in the last generation has these following fitness values, and the kp and ki value. Kp value is on the x-axis, ki value is on the y-axis, and the fitness value is on this axis. And this gives you a good idea of what are the best kp and ki values over here. So definitely the highest over here would be the best. Which one has the highest fitness value with regards to kp and ki? So this gives you a good idea of how your kp and ki values are. The third graph over here is the response of each individual in the last generation. So this is generation number 19, which is the last generation that has been mutated. So we ran the system for 20 iterations, and the last generation is generation number 19, because the first generation was just a starting one. And well, actually this is generation number 20. Sorry, this is generation number 20. Yep. So these are all the individuals in the last generation. And as you can see, most of them are performing well. They are able to reach their steady state besides this particular individual, which I think is either 191 or 198. I'm not sure about that, but we could find that out. And so are the KP and KI values. This one didn't perform that well, but most of these are performing well. And so you can now come up with a good idea of how your KP and KI values should be. Of course, we could further mutate them to get even better values, but with the start of our system response, we will be able to now see that we have now mutated to a good value of KP and KI. The other graph that I wanted to show you is now this one. So this it essentially shows you how our evolution, or how our genetic algorithm was able to come up with better results. So these are the generations over here. So this is the very first generation and its fitness value. And as you can see, as we have mutated our system, our fitness value has increased. So we went from 0.47. So this is the highest fitness of a particular generation. So the highest fitness value that we achieved from our generation number one was 0.47. And so it kept on. So these individuals were used to mutate our system. So you can see that we kept on mutating, and then we kept on having this. So once we reached zero point 0.8, that was our sweet spot. So these values of keeping KPI were good, and then we kept on increasing our value. So we kept on performing well until generation number, I think, 9 or 8. 8 is the generation number where our mutation reached its limit. Further than that, we kept on having some increase, but the increase was not that much. Which means that even if we further mutated this, we will not be able to. We might be able to surpass zero point 0.9 or reach zero point 0.9, but it's difficult to say because of the progress of this. This could mainly be attributed to the fitness value. The way the fitness value is being calculated is either not good enough or not. But still, however, you can see that the mutation is actually happening, and then we are able to achieve our goal within quite less iterations. And again, this is more or less supervised learning because we know how we need to mold our system in order to get a very good value of KP and KI. But still, it took us at least 9 generations to reach a very good value of KP and KI with respect to the fitness value that we have. The next thing that I wanted to show you was the fitness value with respect to the KP and KI. So over here, each dot represents the generation. So this is generation number one, and you can see that the fitness value was 0.59. These were the KP and KI values. And what you can see is ultimately what happens is there's a cluster over here, and so you can now come up with a very good understanding of the highest performing individuals in each generations had KP and KA values close to these. So for example, over here, if you can see, the fitness value over here was 0.85, and the KP value is 8.5, and the KI value is 16. So this is quite significant. If you look at the very first generation, you see that the KP value was 4.3 and the KI value was 16. So it's a major difference now that how we have evolved our KP and KI values. And I'm pretty sure if we have evolved further, there would either be a higher cluster over here, or if we got better values, it would be further down the road. But essentially, we are able to definitely reach our target of having a very good system. The last graph that I want to show you is the response of the best individual in each generation. So in generation number one, you can see that our system was not performing at all well. So you can see that our system was very irregular. And so on, then in generation number two, we were able to reach steady state, but our system had a lot of aberrations, and then so onward. So we went out from generation one to, so these are the best performing individual in each generation. And as you can see that after generation number 7 or 5 or 6, we are now able to at least reach our system. We're performing very well. If we move on to the other individuals in our system, now we can see that from generation 11th onwards, we are now performing even better. Our overshoots are decreasing, and we are now able to at least reach our desired system. So, of course, I now feel like if we are now able to further focus down or further penalize our overshoot, we might be able to even reach better system. But the thing is that settling time right now for these individuals must be really good. So settling time, if we could plot settling time ratios and see that the settling time ratios are now decreasing, which means that even though we have some overshoot, we're now able to reach our desired steady state at less than 4 or 5 seconds, which is quite good, which is very good actually. So this is about it. I think now what I do plan to do is I'm gonna use this to further evolve for like 50 generations and see what happens. And in the next part, now I'm gonna change the reference values as well. So I want to see whether changing the reference point improves or these KP and K values can work for multiple reference values. And then I'm gonna try to change either the PID controller. I haven't thought about it, but I think I'm gonna change the PID controller. So right now we only have PI, but whether we can introduce the derivative term and get over the overshoot problem. But of course, that's gonna produce its new set of problems. How do we come up with a D value, or what is the best D value that we can use? and whether if it is too slow or not. I think so we can also come up with that. Like if it affects the system so much, maybe that's not that worth it, you know. Our error right now, the maximum error is around 20%, but that's just not for that much. So if you consider 1 meter to be your height, you're going 120, like 120 centimeter and then coming back. That's significantly a lot. But if it's an outdoor application, definitely it doesn't matter. But if it's an indoor application, you would like this overshoot to be as minimum as you can. Maybe the cycling time over there can be sacrificed, so you would require your system to be much more slower but reach its desired point safely. So those are my future attempts. So I'm definitely now planning to either see that if I can if these values can be implemented on a quadcopter of a similar model but with different dimensions. That's another target that I am thinking about now, and I will explore that. But I'm not sure about this. So maybe I'll make more videos because this is the last video for the CS206 project, and after this I'm gonna start working on my final report. But it's been quite interesting. It's really has been quite interesting project. Anyways, with this I have come to the end of this video. I hope you enjoyed it. Bye bye.